In this video, we'll be constructing an approximate solution to a differential equation. Let's begin by considering the differential equation y double prime of x plus y of x is equal to 0. In the Taylor series refresher video, I pointed out that we can approximate functions via polynomials, so let's produce an approximation. Let's first plug our function into the differential equation. Computing this, we get 2c plus a plus bx plus cx squared. Now note, this is not equal to 0 unless a, b, and c are all 0, which would then be the trivial solution. So except in this boring case of yx is equal to 0 for all x, we don't have a solution to our differential equation. Let's put some constraints on what our approximation needs to satisfy. We'll introduce the term allowable approximations. We'll call our approximation allowable if it solves the initial conditions of our differential equation. Remember, our differential equation was y double prime plus y is equal to 0. Let's also impose some initial conditions. So these will be y of 0 is equal to 1 and y prime of 0 is equal to 0. From before, our approximation is of the form a plus bx plus cx squared. We want our approximation to be allowable, so let's plug in the initial conditions. Plugging in 0, we get y approximate of 0 is equal to a, which is supposed to be equal to 1 via the initial conditions. Plugging in 0 to its derivative gives us y prime approximate of 0 is equal to b, which via the initial conditions is supposed to be equal to 0. Hence, to be allowable, we get that our approximation has to be of the form 1 plus cx squared. So we still don't know what c is supposed to be. I'm going to introduce a function which we call the residual or mismatch function. It's defined to be what we get when we plug our approximate solution into the differential equation, then take the left-hand side of the differential equation and subtract off the right-hand side. The order doesn't really matter. Left minus right or right minus left, either will work. In our example, well, the right-hand side of the equation was 0, so we just end up with this, which if we compute out is equal to 2c plus 1 plus cx squared. Here's how I want you to think about this function m of x. It is a way to measure how much we failed to solve the differential equation. For example, if we had a solution to the differential equation, then m of x, our mismatch function, would be 0. If we don't have a solution, it spits out a number telling us how far we are from being 0. Let's rewrite our approximation. So we have y approximate of x is equal to 1 plus cx squared. And let's include our mismatch function, m of x, which is equal to 1 plus 2c plus cx squared. A natural question is, how do we choose c? The answer is, it depends on what properties you want your approximation to have. I'll do two examples. In our first example, we're going to ask that we set as many terms of m of x to 0 as possible in ascending order. Well, what does this mean? Well, m of x is equal to, I'm going to write it like this, 1 plus 2c plus cx squared. And there's a secret x to the 0. By ascending order, I mean these terms. So here's a 0 and here's a 2. So starting at the lowest power, we're going to try to set as many terms to 0 as possible. So starting at this term, if we want it to be 0, then that means that c is equal to negative 1/2. And then we're done, because there's no way we can set this equal to 0 since we've already chosen c to be equal to negative 1/2. Then our approximation is of the form y approximate of x, which is equal to 1 plus cx squared, which is now equal to 1 minus x squared over 2.